all you had to really do with that.
I like calculated moles just to realize I didn't have to do that.
So it's
Because
kind of
it was like they gave you P and V, and then with the next people it was like N RT, and I was like, oh, we just figured that out.
Yeah, you didn't really have to do too much with that one. So for this, we had what was it? A container that had there we go, 250 centimeters cubed in it, and then there was a gas. We had two compartments with gases in it. Like that, did I tell you what the identity of them was?
Yeah.
Oh yeah, RG and N2. Argon and then neon, okay.
I think
So-
it's gonna matter.
And then each of these, the left compartment, it was 100 kPa. The right, it was also 100 kPa. And what did we say was equivalent in about this? Or what's the same?
Temperature.
Yep, temperature was the same. Temperature was, I think, 0 degrees C.
Oh,
Yeah.
volume?
Yep, the volume of each of these compartments is the same. So this was state 1. And then we could go to state 2. Where it's just opened up, that partition's removed. A, R, and E, and they're both at the same conditions. Okay, what do we have to assume before everything else? Ideality. Oh, just a fun word to say. Why is this a good system to assume ideality? Yeah, Josh?
Because these are noble gases.
Yep, they're noble gases. That's going to be the best case scenario that you got. Okay, so we were trying to figure out what in this problem.
Entropy, remember energy,
Yep.
energy.
Yep, so we were trying to get delta S mix, delta G mix. Okay, we can do that fairly easily. What equation do you want to use for delta G mix? What's that one?
I used NaRTLN.
Yeah.
P star over P.
Okay, so you used
And then just multiply that by
so you used NaRTLN star over P A
That I just kind of multiply by so
RTLN PB star over PB, right? So that was one where they weren't starting at the same initial pressure, right? So you could do it that way, but you made your guys' life a little bit harder. What if they did start at the same pressure? What?
Oh, you can do like the chi's.
Yep. So you can do the mole fractions. So we can look at N total, chi A, ln, chi A plus mole fraction of B, ln of the mole fraction of B. So that's the way I went with it. If you calculate them, you should end up with the exact same answers, but that way it's just a little bit faster and easier. Since we have a perfect gas, what is going to be the mole fraction of these two? And their pressure is the same. Yeah, both of them are 1/2, right? So they're equal to one another. So all we have to really do then is figure out N total, right?
Well, can you skip that step?
Yeah, you can. Why can you skip that step?
Because PV equals nRT.
Yep.
Which I later found
Yep, exactly. So if we were talking about an ideal gas, nRT is equal to what?
out.
PV. Yep. So our equation can actually change. We can get delta G mix is equal to PV times mole fraction. In this case, we're going to put in our actual gases. Mole fraction of argon plus mole fraction of helium, ln mole fraction of helium. Okay, and we know the mole fraction was what again for each of these?
1/2.
1/2. So now all we really have to do is just plug in our pressure. Kilopascals are okay, so we need negative. Oh wait, we're not having negative down here. Oh, I know why. We don't really need a negative value yet. I did something weird with my outlines. Yeah, it does need to be negative because we are mixing. So 3, we want pascals times our volume, which was what, 250 centimeters cubed. We got to get that from centimeters cubed into something else, get into meters cubed.
Centimeters squared. Cubed is equal to
So 1 centimeter. Oh, so you went with milliliters and then convert milliliters.
Oh yeah,
to
I
liters?
just want milliliters since milliliters is equal to centimeters cubed.
So for every 1 meter, we have 100 centimeters, right? So I just cubed that to get into meters cubed. If we have pascals times meters cubed, what do we get as a unit in the very end? Yep, we're gonna get joules in the very end. Last thing we have to do is do that like 1.5 ln 1.5 plus 1/2 ln 1/2. When you do that, if you have the ln of a number that's less than 1, what's going to be its magnitude?
Negative.
Yeah, it's going to be negative, or its sign, excuse me. So when you do that all through, what I got was negative 17.3 joules in the end. Okay, so that gets us delta G mix. We have to try and figure out delta S mix now. Delta S mix. How is that going to relate to delta G mix?
It's going to be the derivative of delta G.
Yep.
With respect to T.
Yep, you can do it with respect to T. There is another way you could do it too.
You just do the divided by T.
Yep. Delta G mix divided by T, you can take the negative of
I
that.
guess that means too.
Yep, it's the same.
Yeah,
I
I
never
think about
did
that.
the
I
whole
think
thing.
Yep,
the whole
that's fine. It's fine if you do it. It's just going to be more work for you.
Yeah, that's
So you plug that in.
That's very.
What are the units going to be, or what should the units of S be?
Positive.
Yep, it should be positive.
Oh, sorry.
Yes. Joules. Yep, joules per Kelvin, and it's a really small amount, 0.0634, I think. So is that exactly what you guys got?
Yeah.
So you took a little bit harder of a route, but you got to the same answer, which is okay.
Oh, because there's no temperature.
Yep, there's no temperature in the very end, or if we're just taking our G value, we have joules, we're dividing by K, so we should get joules per Kelvin.
And what should it offer on the?
Not much, like 0.5 max. Yeah. Which is one more. Which it doesn't really matter. If you look at the total score of the daily problems, they do add up, but like individually, I think they're less than like 1% of your grade. So individually, they don't make much of a difference, but collectively, they do. Okay. So.
Whichever way you want to look at it.
Yeah, whichever way you want to look at it. It doesn't matter, the universe is going to stop anyways, right? So. Are there any questions about that problem?
December 1st.
Yeah, so. Everybody do okay with that? All right, let's do the next one. The next one you've done, like you guys have done a million problems like this. So, do you want to go through that one or
No.
no? Okay. Do you want just the answer then?
Yeah.
Okay. Concentration. Oh, not concentration. Excuse me. Partial pressure of H2 should have been like 0.42 atmospheres of what's D?
Deuterium.
Deuterium. Deuterium. Yep, deuterium. That was 0.02 ATM, and then yep. It's a watt of hydrogen. Yep, it's an isotope. What's the other isotope of hydrogen? Tritium. Yep. I know it was 3. That's the one in like the third of the older Spider-Man movies, or no, second, the Dr. Octopus was trying to always get. So those are the pressures that you should have calculated.
What was the X value?
The X value I calculated. 0.0833 ATM.
Okay.
Wait, what's me?
Okay. Do we want to go through the manipulation? It's pretty. This one was nice because you didn't have to do the quadratic equation
Because we're just squaring your 2x.
because you ended up with this.
Because you squared the 2x because there's 2.
You got that, so then you can move the x, the 4x over, the x squareds go away, and your life becomes much easier. Okay. Always looking on the bright side, right? Yeah. Okay, so last time we were working on trying to figure out the extent of the reaction. We did a problem similar to this where we were looking at equilibriums. And we were looking at, it was ethyl acetate and water reacting, right, to make, what was it? Acetic acid, methanol, God's gift to the planet. That's what, I think Ben Franklin said that. He's like, here is the proof that God loves us or something. So we had that equilibrium going on, and we figured out the partial pressures of everything, right? So we had those partial pressures, and we ended up figuring out like the equilibrium constant expression. But the next thing we had to do was figure out the extent of the reaction. Okay, what do you know about the extent of all of these species? They got to be the same, right? So let's just pick one that's pretty easy to go with. The one, yeah, I went with water. The reason I went with water is because you know its molecular weight, you know a lot about it, everybody can seem to identify that. So let's try and figure out the extent of water. So what are we going to have in the denominator?
1. Negative 1.
Yep, negative 1. So we need that. Let's write it out in terms of symbols. Yeah, we'll put it over here. Negative 1. Why is it a negative value?
Because it's a reactant.
Yep, we have a reactant in this case. So reactants get negative values. The 1, where's the 1 coming from?
Regular.
Yeah, it's the stoichiometric coefficient. Okay, then what are we subtracting from one another? Yep, so N final of H2O minus N initial H2O. Okay, so we run into a problem with that because we don't have masses at all, right? Because we were talking about a gas phase system, so what are we going to do? What's that?
Well, you like to determine it from like the P total and the partial pressure.
Yeah, you could do that, so you can look at the P total that way. So what do we have to assume? Ideal gas. So that's exactly what we're going to do again. So we're going to PV and RT it. What's that equal to then? Yeah. PV over RT. Luckily, we're told all of that. We're told our temperature. What is our temperature in Kelvin in this problem? Do you remember?
I don't even know the original.
120 + 73.
Yep. So our original temperature. So our volume was 10 liters. Our R, we're just going to keep that as. Let's do. What did we record our pressure in? It was bars.
Bars.
Yep. So what value of the ideal gas constant do we want to use then? We're in bars.
Convert bars to pascals.
You could convert. Yeah. Could convert bars to pascals. Let's just leave it at 8.314 times 10 to the minus 2 bar times liters divided by, what do we got? Mole.
Okay.
Yep, K. And then McKinsey said for our temperature, we get that. Now our pressures are going to be different. We have our initial pressure and our final pressure, right? Our initial pressure, what was our initial pressure for H2O? H2O that was defined for us in our,
One bar.
yep, we had 1 bar. So that makes life easy. So we just multiply that through, and we'll get that. What about our P final for H2O?
Is it 0.667 or was it
It's 0.33.
0.333?
Yep, 0.333. Okay, so all we have to do is plug those values in here. What you'll find is NF of H2O was 0.102 moles, and then Ni of H2O, so the initial amount was 0.306. Sorry, writing's hard. 306 moles. Okay, so we just have to plug those values in. So, what's the sign of our our numerator going to be?
Negative.
Yep, it's going to be negative. So what about the extent?
Positive.
Yep. Okay, so we got 0.306 moles minus 0.102 moles. So it should be positive value. I calculate 0.204 moles as our extent. And luckily, like James said earlier, we know all of our extents are the same, right? So we don't have to worry about going through and calculating the rest of them, assuming we did that one right. Okay, what was so that answers A. In B, we had to figure out what delta G of the reaction was. Does anybody know a formula that can relate delta G naught in like the Q or anything like that?
Isn't it delta G not reaction plus RT on Q?
Yep. RT ln Q. Yep. Okay, how does this expression change if we're talking about equilibrium?
The delta G reaction just changes to 0.
Yep, that becomes 0. Delta G naught is this. And then what happens to Q? Yep, Q becomes K in that case. Okay, so what is going to be our delta G reaction then? At equilibrium.
Negative R.
Yeah, it's just 0. Yeah, it's also equal to this stuff too. But the value of delta G reaction
It's just 0.
is just 0. Because we're at equilibrium, right? However, that's different than delta G naught of a reaction. That comes from tabulated data, which we can all add up and do that. So we could look up delta G naught in the back of the book, sum all the products, subtract off all the reactants, right? But we can work on, well, we know the value of K, so we can actually use this expression to figure out delta G naught of the reaction. So how are we going to manipulate that around?
It's going to be equal to negative RT ln 4.
Yep. ln of K, which is going to be equal to our G naught of the reaction. So,
K is 4 in this.
yep, K is 4 in this case. What do you want to pick for your R value? Yep, 8.314 joules mole K. What's our temperature in this case again? Yep, 390 K or 393 K, and then we have that ln 4.00. Now, when you do that all out, what are your units going to be? Yep, joules per mole. What's the sign going to be? Yep, negative 4.530 times 10 to the third joules per mole. Most of the time, how are delta G's reported though? Yeah, they're usually calculated in kilojoules, but it's not super important. We all know. Okay, cool. Are there any questions about that problem? So a lot of stuff was crammed in there. The most important thing to know is delta G of our reaction is going to be 0 at equilibrium. Delta G naught reaction, however, is not equal to 0 at equilibrium. Okay? Any questions? Okay, so far, when we're talking about delta G and we're looking at the equilibrium constant, we've assumed what?
Ideal gas.
Yeah, we've assumed ideal gas. What do we know about ideal gases?
Bullshit.
Yeah, it's bullshit. It's not gonna work out. So let's see how can we incorporate real stuff into this? How is this actually done? Well, you kind of know with gases. How did we figure out the behavior of a real gas or the pressure of a real gas? What did we consider? We considered composition, but we calculated something. Start with an F.
Fugacity.
Yep, we looked at fugacity. So we're going to talk about activities in fugacity. We already have an idea of what fugacity is. We gave it that funny F symbol. And what was that equal to? Yep, pi. So that fugacity coefficient times what?
Pressure.
Yep, pressure. So that way we could see how the idealized pressure really behaved, and we just threw in this fudge factor to make our lives easy. Said, all right, all the non-ideal stuff, it's just in that coefficient. We don't have to worry about it. We're going to do the exact same thing with activities too. When we're talking about gases, we're really talking about partial pressures. We can look at concentrations, molalities, and a bunch of other concentration terms. What activity? Oh, there's no I in between the T. Is how a solute or gas particle deviates from ideality. Which I think only has one L, but that's all right. And we said that the fugacity changes based upon that activity or that fugacity coefficient, right? So we derived that all the way back couple weeks ago, where we were considering. We didn't talk about chemical potentials at that time, did we? Okay, so let's go back. We talked about it in terms of delta G, but we never discussed really chemical potentials. So let's drop back to that. So we have shown for an isothermal change. Isothermal meaning what?
Constant temperature.
Yep, constant temperature. The delta G was equal to nRT ln EF over PI, right? So we've derived that like a million times. If we express this in terms of chemical potential, or that mu, how was chemical potential different than the Gibbs energy, or how did they relate? Mu is equal to what over what?
Change in G
Yep, change in G over,
the moles.
yep, the moles, the change in them. So what are we going to do to this expression then? What are we going to divide by? Yeah, going to divide by moles. So what is the chemical potential equal to then for this gas? Yep. Yep, PF over PI. Okay. That'll actually be delta mu, right? Okay, we're going to do a similar trick in a minute to what we've done before with that mu naught, or the standard chemical potential. If we're looking at change in mu, it's always what minus what? Yeah. Final minus mu initial. Initial. And let's just make our lives easy. Let's say we're going to start at some constant reference point for our mu initial. So if we initially start at a pressure, what pressure do you think we're going to pick?
1 bar.
1 bar to make our lives easier. So a standard pressure. 1 bar or P naught. Then we can define this as we're going to move mu final over, well, we're going to keep mu initial where it is. We can define each mu as mu naught minus RT ln P final over P naught, right? Okay, and mu is that chemical potential at 1 bar, right? So we've talked about that a couple of times. Okay, so this works for an ideal gas. So what we've done, we've just manipulated this equation around. We said mu is equal to that. This works for an ideal gas. What about real gases? What are we going to have to incorporate in there?
Gasity.
Yep. We need fugacity for real gases. Since our chemical potential depends on the pressure, that's what we need to express this correctly. Okay. So how are we going to change our expression here to represent fugacity?
We can just change our pressure final,
Mm-hmm.
pressure not, to the expression of just fugacity.
Yep.
Divided by your,
Yep. So we're going to get RT. We'll do what Josh said. We'll put fugacity up top. And what are we going to keep in the bottom then?
your little, our partial pressure.
Yep.
Not your partial, just your.
Yep, your standard pressure. Okay. Again, when is fugacity going to behave most like an ideal gas? Yep, when the coefficient is equal to 1, right? What other conditions for an ideal gas?
High temperature.
High temperature, what else?
Low pressure.
Low pressure, yep. Okay, so, let's hop back here for a second. So when we're looking at activities, this portion right here, that's actually what we're going to describe as the activity. So the activity of some species in the gas phase is going to be the fugacity of that species over its standard pressure. So basically, fugacity and activity are the same thing for gases. However, how often as chemists do we really deal with gases?
Not all.
Not often, so a little bit in Echem, right? So really, what do we want to consider? What do we want to find?
Common activity for a solid or
Yeah.
liquid.
Yep, we want to find solid, liquid, and then aqueous solutions or solutes, right? So in order to do that, we're going to have to consider the chemical potential of liquids. And the first thing we're going to have to do is consider a container with a gas liquid at equilibrium. So in this case, what we're not talking about like a chemical equilibrium. What we're really discussing is the equilibrium between two phases. So let's say we have a closed vessel and we put some water in there. H2O liquid. What's going to happen if we let that sit there? So we instantaneously put that in, we let it sit there for a little bit. What's going to happen?
Some will evaporate.
Yep, some will evaporate, right? This water level is going to go down a bit. And where do those go?
Into the air.
Yep, so we get H2O gas, right? Are the gas particles always staying as gas particles and the liquid particles always staying as liquid particles? No, there's a constant flux between them, right? So some of them are bopping out, they have enough kinetic energy to escape the intermolecular attraction forces, they go into the gas. Some of the gas particles run out of energy and then eventually fall into the liquid, right? So we get that sort of equilibrium happening back and forth. Now it's kind of interesting because you can like just look at a bottle of water and think nothing's like, it's nothing fantastic or anything, but there's really a bunch of stuff that's going on there. Okay, so what we're going to say then is mu of the vapor is equal to the chemical potential of the liquid. However, this is kind of boring because we're only considering one compound, right? So how does this change? We're going to ask the question, how does this change with the change in composition? So we're going to fall back to talking about ideal solutions first, then we're going to move into activities and see how do these things really behave. So the next section is ideal solutions. Okay. What we're going to do, we're going to have to add a new bit of notation. We're going to add the star notation. Or however you want to draw that. So whenever we see that, we're talking about a pure substance. Therefore, if I were talking about mu star A, what are we really talking about?
Chemical.
The control.
Yep.
Control.
Yep. Chemical potential of puree. Puree gets pureed. Okay, and how is this chemical potential defined? So if we add solute particles, we then get mu A, right? So we're no longer at mu A star. We get mu naught sub A plus RT. And then we have, what else are we going to have, or what was that last term for gases? It was Ln.
Well,
Yes.
it's a net,
Yeah.
it's just P star.
Yeah, it'd be P star over P naught, right? We're just going to switch that P star A. So we're going to have that standard chemical potential of A, and then we're going to look at pure A. All right, that'll never go. Oh, I'm sorry. This is not for solute particles. What is this for?
This is for a regular pure substance.
Yep, this is for pure substance. What about if we had solute particles? What's going to change in that case?
You're gonna add on another.
Well, mu is no longer mu star, right? It's just mu sub A. What else are we going to get? Yep, mu naught A plus RT ln of what? We could do it in concentration. Let's stick with the vapor pressure for now.
Is it a fraction?
No, I don't need a fraction yet. Yep, just PA. Okay. So we're gonna do something fancy here. What do both of these terms have in them? That's gonna be a, what's that?
Mu naught.
Mu naught, yep, and mu naught A is gonna be the same for both of them, right? And we're gonna use that to figure something out. So since the standard chemical potential and what do we denote as the standard chemical potential?
Mu naught A.
Yep, mu naught A is the same. In both equations. Then let's set those equal to one another. Okay, how are we going to manipulate this one around to solve for mu naught?
Just throw.
Subtract.
Yep. So we got mu naught, or mu star A minus R T ln P star A, right? So that's equal to mu naught. What about that one? What's that one going to be?
Mu naught, or mu A
Mm-hmm.
plus RT ln B A.
If we,
Minus RT ln B A.
yep. Okay. We're almost there. Which of these mu's do we care about more so, or which one are we trying to find out if we're talking about a solution with solute particles in it? Mu A. So how about we might isolate mu A and see what we get? Okay, so let's manipulate this around. We get mu A. What's mu A going to be equal to?
Just mu star A.
Yep, mu star A.
Or the ln of P star A divided by PA.
Oh, you're skipping steps. Yeah, I think which one is it? We got to move this over so we get plus R T ln PA star ln. Is it? Well, no, because we moved. Oh yeah, you're right. Yep, because all we did was move that over. There, yep. Where? There we go. Okay, now let's do what Josh wanted to do. We'll combine it all together. Using the properties of logs, what's it going to be? 1 over what? ln.
PA.
Yep. Okay. Woo! Okay, so we're looking at, this is our vapor pressure of our solution with those solute particles in it. This is that of our pure solution, right? So we're kind of looking at a ratio of those two things. What did we do with gases when we were talking about like delta G mixing? What did we distill that sort of down to? Or like when we were looking at, what was it, delta G mix, we could look at each individual amounts of moles, right? Or we could look at a mole fraction. Let's try and find a mole fraction in here. So we can relate the mole fraction of A. Using, you remember from general chemistry which chemists or physicists could we refer to?
Beer.
No, yeah, we could always refer to beer. That's a good bet. But it had to deal with vapor pressures of solutions.
Is that really hard name?
Starts with an R.
No.
Raoul. Raoul's law.
Yeah, we talked about him.
Yeah, we talked about him. So we said if we were looking at the pressure of A, what did we have to multiply that by? Or what? How could we figure out the partial pressure of A?
Wasn't it? No, I don't know.
Just P total times chi of A.
Yep, it was P total times chi of A. Or let's say we wanted to look at the individual component. So we could look at it in P total, but we could also look at chi A times PA star. So we could look at the total pressure, or we could consider that species by itself times its mole fraction. Okay, what's mole fraction equal to then?
P A star.
Yeah, PA over PA star. See that somewhere before?
That's not how that works.
Yeah.
Mole fraction of A, that's cool.
Yeah, that's real cool.
That's,
That was awesome. Yeah, it was cool. Yeah, so then mu A is equal to mu A star plus RT ln of what?
your mole fraction.
Yeah, mole fraction, which is awesome because it is awesome because we're out of pressures. We're now talking about mole fractions. Okay. Let's hop back through a little bit. Let's get to activities. So back to activities. So we've talked about this. This is for a mixture. So in order to represent the behavior of real solutions, we have to consider activity. We've shown for an ideal solution that this is true, right? We've shown both this, so for ideal solutions, we could represent that A star plus RT ln P A over PA star, or we could represent that with mole fractions, right? But the downside is we use Raoult's law. Not all mixtures follow Raoult's law. Of course not, because that'd make it too easy, right? So, however, not all mixtures follow Raoult's law. Which I think I've spelled his name like 4 different ways. Okay, so we have to introduce activity. So activity has got to be introduced. What is the simplest way that you can see that we can just deal with this problem? So these are for ideal solutions. How are we going to incorporate activity?
Throw in
Throw in a
an
constant.
extra term.
Yeah, we could throw in an extra term. That's always a possibility. That's going to make it a little more complicated. We could throw in a constant somewhere, a fudge factor, and that's what we're going to do. Where is the activity going to go, though?
The ln.
Yeah, the ln. We're going to put the activities in there. So, mu a is just equal to mu a star
Doesn't have to-
plus RT ln activity of a.
Everything goes in the ln.
Okay, and so if we're talking about mole fraction, so to involve mole fraction, what we can do is say activity of A is equal to this gamma term times mole fraction of A. And what's that gamma term? Yeah, that's our fudge factor, that's our constant. This is going to be our activity coefficient.
And does an activity coefficient change between solutions?
Yes, and it changes depending on what you're considering. So that's the one for mole fraction. We can have an activity for concentration. So in that case, it is still the activity coefficient of A, but we give it the symbol C. So this A is for the, let's represent it this way. Let's do I sub I times the concentration of
This is
I.
activity for concentration.
This is the activity for concentration. So that activity coefficient is going to change. It changes to different values.
Instead of using mole fractions, we just use concentrations.
Yep. So that C stands for concentration. We could do the same thing for molality. Where we're considering the activity of I, it would be the mole fraction of I using its molality coefficient. For some reason, we give molality the symbol B
Which is
times the molality of B sub I. So there are different ways. Do you remember what molality was? It was something over something.
Like grams of solute over liters of solution or some nonsense.
Yeah, it's some nonsense, right? It was kilograms of solvent in the denominator. What was up top? Yeah, moles of solute. And if you look in your books, most of it deals with molality, which, like James said, is nonsense. But that's originally how they started looking at activities. So we can relate it to concentrations. But just keep in mind that all of these activity coefficients, depending on what you're talking about, change value. So if, for example, if someone says the activity coefficient is 0.0 whatever, ask them, is that for concentration, is that for molality, or is that for mole fraction? Because there are many activity coefficients that you can have. Most of the time, as chemists, where do we always fall back to?
concentration.
Concentration, yep. Some physicists consider molality more so. Mole fraction really only ever is important for which systems?
Closed system.
Yeah, that's true. Mainly gases, because it's a little bit easier to deal with them that way. So next time, we're going to talk about how activities are involved in that equilibrium constant, and how we can use this sort of stuff and where do these activity coefficients come from. And after we figure that out, we're done with thermodynamics and we're going to talk about kinetics. Okay? Yep, we have a Quizlet on Friday, so prepare.
It's all of this on it.
All of this is on it. I will have to double check. There's probably nothing too intense with this stuff like that we covered today. But let me double check. I'll send an email out about it. Okay? So just be sure to prepare your sheet. You do have a daily problem that is due. We haven't quite gotten to everything relating to it yet, but it's dealing with the activity of a pure liquid. What do you know about the activity of pure liquids and pure solids?
The coefficient.
Yep, the activity of pure solids and liquids is equal to 1. And you're going to have to prove that. Okay? All right? It'll totally be self-explanatory. If not, just email me, okay? All right, are there any questions? Yeah, what's up?
I'll do this down there.
I didn't understand how we just.
Oh, the gasity? Because we were talking about an ideal gas in this case, and then we wanted to go for real gases.
Okay.
So we showed kind of in the past that if we were considering delta G, if we wanted to look at delta G of a real gas, instead of considering PF final, we have to consider the fugacity.
Okay, so essentially just fugacity.
Like we could put fugacity at a standard pressure over the fugacity of some other thing, but this pressure is so low, and by the way that we've defined fugacity, it depends on a reference state.
Okay.
So, like if we said fugacity naught and P naught, they're the same thing. Okay? Does that make sense?
Yeah.
Okay, cool. So we're almost there.